So welcome back to our discussion for continued discussion on boundary layer theory. And in the last lecture, we saw how to obtain approximate solutions to Prandtl's boundary layer equation by considering an integral version of that equation, which gave us one common momentum integral, and then assuming an approximate form of the velocity profile using basically a fitting version of the velocity profile, we were able to obtain things like boundary layer thickness, skin friction, etc. for the flat plate problem. Now, in general, going back to the boundary layer equations that we have been extensively studying over the last couple of lectures, this would be the general formulation for our boundary layer equation coupled with obviously the continuity equation that we have from Prandtl. And this is irrespective of whether it's a flat plate problem or anything else. So, I am not saying anything here regarding explicitly what the pressure gradient is. Now, at the surface of the body, we would have the left hand side, which is u dou x, v dou y. It is equal to 0 because of no slip and no penetration boundary condition. So, u is equal to 0, u at y equals to 0 for all values of x is equal to 0, and so u at y equals to 0 for all values of x is also equal to 0. So, in today's lecture, we will actually try to see what is going on near the surface, what is exactly happening near the surface, and what role does pressure have to play regarding what we see towards the surface. And this brings us to what is probably the theoretically the hardest, but in terms of an application point of view, the most relevant question, that when does the boundary layer stop remaining attached to the surface? Will the boundary layer forever actually remain close to the surface, or is there a possibility of the boundary layer actually getting detached from the surface? So, to understand this, so the topic for today is we are going to study the role of pressure gradient first, and then we will discuss about separation. So, at the surface of the body, because acceleration is identically 0 from my no slip and no penetration boundary condition, I have my equation as mu dou square dou y square at the wall is equal to dou p dou x. The viscous force at the wall is exactly balanced by the pressure gradient because there is no acceleration at the wall. The fluid acceleration at the wall exactly vanishes off. We have been touching upon this idea and even in previous discussions that when we are evaluating at the wall, the acceleration goes to 0 and you will always have a direct balance between the viscous effects and pressure gradient. So, now if you use the external stream, so Prandtl's theory tells us that dou p dou y is equal to 0 within the boundary layer, which means I can use the information from the external stream. From the external stream, I have dou p dou x is minus rho u infinity du infinity dx. So, we will consider two scenarios. One, when we have an accelerating flow. An accelerating flow is where du infinity dx, or actually ddx of u infinity square, the magnitude is basically increasing with increasing in x. So, if I am looking at a flow along the positive x direction, if the stream is moving in the positive x direction, it is continuously getting faster and faster. Or if the flow was in the negative x direction, it is continuously becoming faster and faster in the negative x direction. So, that is the definition of what would be an accelerating flow. In the direction of motion, the speed is increasing. So if this is positive, I have a dou p dou x as negative, right? This is known as a favorable pressure gradient, and you will see very soon the terminology favorable. Why is it used so? Why are we attaching an adjective to the pressure gradient? We can just say that there is a negative pressure gradient where pressure drops as we keep moving along the flow, which means I am moving from a region of high pressure to low pressure. I could have just said that, but right now I am giving a qualifying adjective calling it as a favorable pressure gradient. In contrast to when you have a decelerating flow, I will have ddx of my u infinity square is going to be negative, which means if the flow is in the positive x direction, it decreases as you move along the stream. If you remember this discussion from even Faulkner-Scan families, we had classification of flows that were increasing with x or decreasing with x. So there can be a lot of kind of flows where the flow is in plus x direction, but as you keep moving to larger and larger values of x, the flow is slowing down. So that's a decelerating flow. If the flow is decelerating, dou p dou x is positive, which means pressure is continuously increasing in the direction of the flow, and this is known as an adverse pressure gradient. Once again, we have attached an adjective here. So we'll see what's the consequence of this. So if we take the accelerating case, I'll label that as case 1. In the accelerating case, I have a pressure gradient that is negative, which means mu dou square u dou y square at the wall is negative. So dou square u dou y square is basically the gradient of shear stress or the curvature of the velocity profile. So this is negative at the wall if I have an accelerating flow. If I have a decelerating flow where dou p dou x is positive, at the wall my curvature or gradient of shear stress is positive. Now the reason this becomes important is in either of these two problems, dou square u dou y square at the edge of the boundary layer, what should the sign be? So think of this, at the edge of the boundary layer there is a u infinity and the boundary layer velocity is smoothly transitioning to the external stream, which means if you are measuring the slope obviously vanishes. We discussed this also when we were doing the one common momentum integral approach. We said that one of the boundary conditions we applied at the edge of the boundary layer was that the slope should go to 0. du dy should go to 0 at the edge of the boundary layer. But a function can go to 0 from the positive values or from negative values. So the fact is, what would be the sign of du dy just below the edge of the boundary layer? So if you look at this, if I am measuring the slope, gradually the slope is decreasing, which means as I approach the edge of the boundary layer, the slope gradually goes to 0. That means as the slope goes to 0, it is decreasing, which implies that at the edge of the boundary layer, dou square u dou y square should be negative. The gradient of your slope or your shear stress should be negative at the edge of the boundary layer, because your boundary layer velocity profile smoothly gets connected to your external stream. So as it gets smoothly connected to its external stream, the shear stress or the velocity gradient vanishes. It vanishes by decreasing from a non-zero value to a zero value, which means that dou square u dou y square or the curvature should be negative at the edge of the boundary layer. This is applicable whether you have an accelerating flow or a decelerating flow. It doesn't matter. So what do you see? If you have an accelerating flow, the curvature is negative at the wall, the curvature is negative at the edge of the boundary layer. And possibly we can assume that the curvature remains negative within the boundary layer. Whereas here, when you have a curvature that is positive at the wall for a decelerating flow, it has to go through 0 somewhere. So dou square u dou y square has to go to 0 at some location within the boundary layer. That is the point of inflection. So there is a point of inflection in a decelerating flow where you go from a case where the curvature is positive near the wall. Curvature positive means the slope is continuously increasing as you keep going up. It starts from a small slope and the slope is increasing, and then it arrives at a negative curvature or a zero slope. So what should it look like? Let's try to sketch. So accelerating flow, decelerating flow. Accelerating flow implies ddx of u infinity square is positive, this implies ddx of u infinity square is negative. This implies from my Bernoulli equation that dou p dou x is negative. This implies my dou p dou x is positive, which further implies that mu dou square u dou y square at the wall is negative. Here you have mu dou square u dou y square at the wall as positive. So if I sketch the velocity profile in the accelerating scenario, it will start from something like this and transition. So if you are measuring the slope here, the slope is continuously decreasing. So this is u by, let's say, u infinity, this is coordinate y by delta of x, and this is u by u infinity of x. So at any point, if you are computing what is your slope, which is dou u dou y is negative. It's continuously decreasing as you go from the wall. So if you are measuring the shear stress is basically decreasing as you go from the wall all the way to the edge of the boundary layer. Now let's contrast this to the decelerating problem. In the decelerating problem, I will have something like this. Here, once again you are plotting u by u infinity of x. So as you approach the edge of the boundary layer, here dou square u dou y square is negative, right? But at the wall, your slope is actually increasing, which means there is some point of inflection where the curvature goes to 0, which is occurring somewhere in the domain. Whereas here, dou square u dou y square is negative everywhere. Actually, this should be dou square u dou y square. The shear stress will always be positive, but the curvature is going to be negative in the accelerating flow throughout the boundary layer, whereas in the decelerating flow, the curvature is switching sign. So, there are few things which you start thinking of from here. One is, when you have a flow that is decelerating, you are approaching a scenario where the shear stress at the wall can start to dip. It can start to dip because you are having the curvature being positive, which means it has to increase. So, from the wall, the curvature is basically increasing, which means the slope has to increase from the wall. So, gradually there is a possibility where the slope at the wall can become significantly small. Now, what are the consequences that we are talking about here? If I take my mass conservation equation, mass conservation tells us dou v dou y is minus dou u dou x. That is just continuity. If I integrate this, v of y is minus 0 to y dou u dou x dy. Now, how do we generate v, or how do we increase v in the boundary layer? It is happening due to viscous diffusion. Viscous diffusion is basically what is responsible for the transverse or the wall normal velocity. But here you can see that if you have a decelerating stream means minus dou u dou x is positive. If the stream was decelerating, then advection will also give you substantial increase in vertical motion. If you just look at mass conservation, if you focus on this particular thing, this is just from mass conservation. If I have a stream that is slowing down, it has to be compensated by faster moving fluid going up, right? If there is a fluid that is gradually getting slowed down, then obviously I need a compensatory faster moving fluid going up. Think of this, you have streams, I am drawing arrows to the length of the arrows are indicative of the magnitude. So, I have a velocity field which is getting slower and slower in the direction of motion. Automatically, to satisfy mass conservation, the only way this can be compensated is that I am bringing in more fluid. I cannot violate mass conservation. I am bringing in more fluid in x. So, if I do a control volume here, more stuff is coming in here than what is leaving in from here, right? So, if dou u dou x is negative, I should have a compensatory faster moving fluid going up. So, this is when dou u dou x is negative. In contrast, if you have the streams getting faster, you have an accelerating flow, dou u dou x is positive, then this requires fluid to be sucked in, right? This has nothing to do with any asymptotics or any other complicated ideas. This is just plain mass conservation. If I have a stream that is getting more intense in the direction of motion, it is getting faster in the direction of motion, I require a compensatory flow to come in perpendicular to the direction of motion. This is just an idea coming from mass conservation. Whereas, if I have a decelerating flow, I would require the flow to move away from the surface. There is a surface here. So, there should be a flow that should go away from the surface. Now, to this picture, you need to add viscous diffusion. With this mass conservation picture, you add viscous diffusion. So, viscous diffusion will obviously want the vertical velocity to spread out. It will allow for more transport to occur. So when you have an accelerating flow, the advection and diffusion are opposing each other. If you remember this, when we did Faulkner scan and we did a flow that was u proportional to x, a velocity profile that was linear in x, what was the boundary layer thickness? The boundary layer thickness was constant. When we computed delta of x, if you go back to your, it's not that hard to check. What is delta of x? Delta of x is square root nu x by u infinity, and we use the same funda when we did u infinity being a function of x. We said let's use the same idea. So if u infinity is proportional to x, what is the boundary layer thickness? It's a constant. It doesn't change with x. So there is an exact balance between the acceleration or the advection with viscous diffusion. There is a perfect balance. If you make the fluid move any faster than x, if you have ux going as x square, then you can see what happens to the boundary layer thickness. The boundary layer thickness is getting thinner as you go in x, because the advection is now dominating over viscous diffusion. In the same way, now if you do the other scenario where u infinity of x was decreasing as you moved in x, then delta of x will continuously keep increasing. It will increase faster than root x. Delta of x goes as root x when u infinity is a constant. There is neither an acceleration or a deceleration. But if there happens to be deceleration, then the viscous diffusion now has another friend to spread transverse momentum, and that is advection. So advection and viscous diffusion are going to act together to make the boundary layer grow even faster than it would have done just purely due to viscous diffusion. So when we did a flat plate boundary layer, there was no acceleration in the problem. The stream was identical at every location in x. It was a zero pressure gradient flat plate boundary layer. So u infinity was a constant in the external stream at different x locations, which meant that the only way that you are having the transverse momentum transport is through viscous diffusion, because there is no acceleration in the problem, right? Now what you have is, when you are going to get a flow that is getting slowed down in the external stream, then you will have an increased vertical transport. So the picture is, if I draw the boundary layer and this is delta of x equals to root x, which we got in the zero pressure gradient flat plate boundary layer, it will become thinner for accelerating flows and it will get thicker for decelerating flows. So we learned two key ideas here for decelerating flows. The two key ideas are, the first fact that the shear stress at the wall starts to decrease for decelerating flow, because you have a case here where the curvature is opposite signed at the plate than the accelerating scenario. In the accelerating scenario, the curvature is always negative, which means that the maximum shear stress is going to occur at the plate or at the surface. Dou square u dou y square can be written as dou y tau wall by mu, right? It is a gradient of wall shear stress, or not wall, I mean just the shear stress. So if dou square u by dou y square is going to be negative everywhere, that means I am going to monotonically have a decay in my shear stress, with the wall shear stress basically being the maximum shear stress in the problem. Whereas here, dou y of tau by mu is going to be 0 somewhere at some location. Let's call that y star. So, at the wall it is positive, which means shear stress is going to increase away from the wall, attain a maximum and then decrease. If I am plotting the shear stress, the maximum shear stress is going to occur away from the wall, which means there is a possibility of the shear stress at the wall getting low enough that it actually becomes 0. And the second idea that we saw here is that when you have a decelerating flow, the boundary layer thickens because there is an increase in the vertical velocity. The vertical velocity is becoming much larger than it would be for the accelerating scenario. So, this brings us to the key point, that what is the consequence of all of this? Because if you go back again to your Prandtl's equation, Prandtl's equation are derived under the assumption that V by U, is this large or is this small? For Prandtl's boundary layer theory, the transverse velocity or the wall normal velocity by the streamwise velocity, is this a large quantity or is this a small quantity? It is a small quantity. In terms of Reynolds number, this is actually 1 by root REL. So, the vertical velocity away from the plate is asymptotically smaller than the streamwise velocity. So, now when you have this decelerating scenario, we are saying that the vertical velocity will get larger. So, as it keeps getting larger, the vertical velocity, as it keeps shooting up, in the context of Prandtl's equation, where you write down in the context of Prandtl's equation, there is a vertical velocity that is sitting here. And what we are saying, that when we see a decelerating flow, there is going to be an increase in vertical velocity. So, as in this problem, as vertical velocity keeps getting larger and larger, you will eventually arrive at a scenario that based on the predictions of Prandtl's equation, vertical velocity is going to become infinitely large. Because if you have this and you are saying that vertical velocity becomes very large, then as per this particular theory, vertical velocity needs to become infinitely large for it to become comparable to the horizontal velocity. Because as per Prandtl's theory, vertical velocity is asymptotically smaller than u. So, the magnitude of the vertical velocity has to become infinitely large for it to get comparable to your horizontal velocity, which means that your dou v dou y, which is the vertical velocity gradient in the y direction, this also will blow up at some point, at some location x equals to x naught, it is going to blow up. Now, if you see from mass conservation, what do you get then? Dou u dou x plus dou v dou y is equal to 0, that should be satisfied, we cannot violate this, which means dou u dou x should also become infinite. If I arrive at again this is all prediction based on Prandtl's theory. Based on Prandtl's theory, the vertical velocity continuously keeps increasing for a decelerating problem. It increases to an extent where as per the equations of Prandtl, your vertical velocity becomes infinitely large. If your vertical velocity and vertical velocity gradient in the y direction becomes infinitely large, that means dou u dou x should also become infinitely large at that particular location where vertical velocity is diverging. So, now if I write this in a different way, rather than treating velocity as a function of the coordinate on the plate, let's treat the coordinate on the plate as a function of velocity. So, this is infinite at x equals some x naught. Now, what I will say is that dou x dou u is 0 for u is equal to some u naught of y. So, there is some point at which the vertical velocity blows up. At that location, the streamwise velocity takes a value u naught of y at that x equals to x naught. So, now I am writing dou x dou u is equal to 0 at that location. So, if I do a Taylor series expansion of x about x naught, this should be x equals to, so x is a variable of u now. I am writing it in a slightly different way. We are always been treating velocity as a function of position. Now I am treating position as a function of velocity, given that there is a certain value of velocity u equal to u naught. So, now if I do a Taylor series expansion, this becomes x equals to x naught dou x dou, so x equals to x naught is the value of x when u is equal to u naught. This is dou x dou u, u equal to u naught, x minus, sorry, u minus u naught, right. I am just doing Taylor series. Then I will have a constant u minus u naught square. What is this term? What is the second term? Zero, which means the point where vertical velocity is blowing up is described by x equals to x naught plus some function of y u minus u naught whole square. Now, if you write this equation in terms of u, you are going to get u is u naught of y plus some function of y square root x naught minus x. As I am approaching the point x naught, the velocity is basically going to be given in this manner. Now, you can substitute this into Prandtl's equation. Once you substitute this into the governing equation, you will find that this turns out to be a numerical constant by 2 du naught dy. So, du naught dy is the value at x naught, which is also a function of y, square root x naught minus x, and the vertical velocity is going to be a u naught of y square root x naught minus x. This is the leading order version of these equations. By leading order, I mean that very close to the point where the vertical velocity blows up. You can see that the vertical velocity is diverging. The vertical velocity is blowing up as you approach the point x equals to x naught. Now, irrespective of everything that we do, u at all values of x for y equal to 0 and v for all values of x at y equals 0 should be, what should be the value? 0. No slip, no penetration cannot be violated, which means if I substitute into this equation for v equal to 0, what do I get? U naught of 0 is 0. If I substitute here, I get u naught of 0 should be 0. And if I substitute it now here, what do I conclude? Du naught dy equal to 0 is equal to 0. This is a result that comes from Prandtl, that there is a point on the surface. So, if I measure along this x, the flow is decelerating, and there is a point at the surface x equals to x naught where your shear stress goes to 0, and that is where the flow stops being attached to the surface. So, what it is going to look like now is there is streamlines which will stay close to the boundary layer, and because the vertical velocity here has become so large that it stops remaining confined to that thin region close to the surface. It remains confined away from that point, but once it approaches that point, it can no longer remain confined, because we have this idea that based on Prandtl's theory, the vertical velocity has become divergent there. The vertical velocity has blown up, and as the vertical velocity blows up, fluid gets transported into the bulk. So, viscous diffusion, which is actually as per Prandtl's theory going to remain confined very close to the surface, stops remaining confined to the surface and penetrates into the bulk beyond this particular point. So, this is known as the point of separation, which is the criteria being that your wall shear stress at the point of separation is equal to 0. So, usually when you read about point of separation, it starts off with this argument that point of separation is where the wall shear stress is 0. So, what we did here, we try to arrive at that result. We try to arrive at this result by basically saying, we know that vertical velocities are going to increase. Decelerating flow has these two consequences. The shear stress at the wall is decreasing and the vertical velocity is increasing. So, as the vertical velocity keeps increasing without any bound, at some point the vertical velocity as you move along the surface is going to become infinitely large. So, when I use these terms infinitely large, I am viewing them again within the confines of Prandtl's theory. For full Navier-Stokes, there is nothing that is blowing up. Within the confine of Prandtl's equation, the vertical velocity is blowing up. If the vertical velocity were to blow up, then at that location, I should require not just the velocity to go to 0, because on the surface, vertical velocity and horizontal velocity both should vanish. No slip, no penetration cannot be violated, which means not only should the tangential velocity or the streamwise velocity vanish on the surface, its slope should also vanish. du naught dy should also vanish, which is the condition of wall shear stress going to 0. So, this is effectively, now if you look at these solutions, what do you observe about these solutions? What is so peculiar about these solutions? It is not just any divergence. What is so strange about these solutions? What happens when x is larger than x naught? It loses meaning, right? You are taking a square root of a negative number, it loses meaning. So, the solution does not have any physical meaning beyond x equals x naught from here. So, effectively the point of separation, mathematically speaking, arises as algebraic singularities of Prandtl's boundary layer equations. There is a price to pay. We had this elegant theory from Prandtl that came from Navier-Stokes, but the elegance that we got, the simplification that we got also brought in this feature that these equations suffer this kind of a singularity, and that mathematical singularity that you have physically manifests as the point of separation, which means beyond this particular point you are going to get streamline pattern which will have a backflow characteristic, that the flow that will come close to the surface will bend near the point of separation and meet the separating streamline. So, this is what typically happens in a lot of problems, that when you have a separation, it is associated with the formation of eddies. So, especially when you do a steady problem, when you are looking at a steady problem and you have a flow, going back to a circular cylinder problem, you are going to actually see a flow in the real problem going from what we have done in class, where there would be these recirculation zones that will form. The streamlines are not going to remain attached forever. It loses the ability to remain attached. You think of the streamlines moving close to the surface, but there is constantly increasing vertical deflection. With this, what we are saying is that the vertical velocities are increasing. So, as a streamline or as a fluid parcel is moving close to the surface, the amount of vertical velocity it experiences continuously keeps increasing in a decelerating flow, and after a point it is just not able to stay close to the surface and it departs off entirely, it takes off. So, the picture in conclusion, we already have a problem that we have done, which is the circular cylinder. In the circular cylinder problem, we wrote down the surface stress as, the surface pressure as the following. So, we had the circular cylinder, theta was measured from here, this is x, this is y, there is a uniform stream in the problem. Now, instead of measuring theta from plus x axis, if I measure an angle here alpha from the negative x axis, which is from the stagnation point that I have, the leading stagnation point, then alpha is pi minus theta. So, I can write my Ps as P infinity plus half rho u infinity square, and it will be the same 1 minus 4 sine square alpha. And the surface velocity is 2 u infinity sine alpha. Right? These are potential flow results. So, what is the pressure gradient? Dou Ps dou alpha is dou alpha of P infinity plus half rho u infinity square 1 minus 4 sine square alpha. Alpha is measured from the negative x axis right now. So, this will be minus 2 rho u infinity square sine 2 alpha. So, if you remember, the profile for pressure or the pressure coefficient looks something like this. This is my Cp, Ps minus P infinity by half rho u infinity square as a function of either theta or alpha, right. So, when you are moving, so if this is the leading edge or the leading stagnation point here, stagnation point 1 and then stagnation point 2. So, I have stagnation point 1 and stagnation point 2. So, when the flow is moving from alpha equals 0 to pi by 2, what kind of a flow does it observe? us is 2u infinity sine alpha. Now you can think of as the external stream, that potential flow. Now you can view this as the external stream. You are going to see an accelerating flow in this stage, right? In this case, your dou ps, dou alpha is negative, because sine 2 alpha is positive between 0 and pi by 2. And once you have crossed pi by 2 to pi, it becomes an adverse pressure gradient and the flow is decelerating. So, how we were discussing earlier, the streams, the boundary layer thickness should actually start to get squeezed as it moves towards pi by 2, and then it will spread out as you go towards the second stagnation point. Because in the second quarter, it is experiencing a decelerating flow. So, this tells you that when you have a flow over a circular cylinder, you will experience formation of a wake due to the separation. Because one part of the flow, the streamlines that are coming are accelerating. But then when it goes to the other half, it is actually now decelerating and it cannot continue to the second stagnation point. This is like an analogous example which I like to give is, think of a bowl and you put a marble inside the bowl. You release the marble. Due to the gravitational potential, the marble is going to come down, come to the lowest point, and then with that kinetic energy that it has, it climbs exactly to the opposite side if it is a symmetric one. Now, if there is friction, this is when it is a perfectly smooth bowl. If there is friction, the marble will come down, but it will not manage to rise exactly the same distance on the other side, right? When it is rising up, then it is not possible for the marble to exactly go the same height from which it was released. So, that in some sense is like separation that is happening, because it is not able to trace the same path. So, when you think of a fluid parcel that is moving over the surface of cylinder, it is like the marble in that potential well, which is frictional, that it slides over it, goes to pi by 2, and then when it is falling over, or in this case it is trying to rise, it is rising against the potential energy. In our fluid mechanics problem, it is basically in an adverse pressure gradient. The pressure is in the pressure gradient is in the opposite direction to your motion. You are trying to move towards stagnation point 2, but the pressure is higher in the stagnation point 2 than at your location. So, you are in opposing traffic with friction being there. If friction was not there, you would have nicely smooth slided over and gone to the stagnation point 2. But because there is friction, it becomes impossible for you to go all the way to stagnation point 2 and eventually you separate. So, what you can do, you can take this entire example of what we have here and try to calculate the wall shear stress and the separation using von Karman momentum integral. It is a slightly more detailed calculation, but that is how people had initially started doing the calculation, that what would be the boundary layer thickness, because the boundary layer thickness is going to diverge at the point of separation. If you see this picture, if you are measuring the boundary layer thickness, let us say you consider the displacement thickness delta star. So, shear stress goes to 0 and delta star is going to become infinitely large, because the streamline gets displaced infinitely. So, you can take this cylinder problem using the velocity profile that we have written down and get an approximate answer of where should the separation actually occur. This is how, the earliest attempts were actually made to understand separation. Once that was done, the first conclusion was that the separation should happen exactly at the point of minimum pressure at pi by 2. But when experiments were done, experiments found that it actually was occurring somewhere here, a little before in the accelerating zone. So that was a little surprising, because you found from experiments that the point of separation for the cylinder was slightly in the accelerating zone, contrary to what the theory was predicting. And then when full calculation was done, it was found that the minima of pressure was not exactly at pi by 2, it was a little before pi by 2. So it was consistent with the fact that it was not in the accelerating zone. Okay, so that's I mean, more or less the discussion that is required for separation. Separation by no means is a trivial thing. It's very hard, as you have already seen, how one goes about addressing this, how one goes about finding it is quite challenging. But the key ideas that should be taken away from this entire discussion is that the fact of separation is associated with flows where there is deceleration that is happening. So when you have deceleration, the two things which you have to keep in mind is deceleration is associated with large amount of vertical transport away from the surface. Vertical transport obviously happens due to diffusion, but vertical transport due to advection is characteristic of decelerating flow. So the boundary layer gets even thicker than it usually would have. And the second point is, when you have a decelerating flow at the wall, the gradient of shear stress is positive, which means that there is a possibility for the shear stress to actually vanish at the wall. And so then we tried to do this calculation, this proof for the velocity gradient going to 0 using this. The details of this was done by Landau. It's a slightly more detailed calculation, but it finally concludes what we always know or always have been learning, that wall shear stress vanishing is the symptom of there being separation in the problem.